We are deriving the bending equation, and in bending equation we are trying to relate. We are finally at the end. We will try to derive an equation which is actually given by, which is actually given as m by I is equal to sigma b by y is equal to e by r. This is the equation we are going to derive, where m is the bending moment applied, and I is the moment of inertia of the beam, and sigma b is the stress at any fiber which is at a distance y from the neutral axis. E is the Young's modulus of the material. R is the radius of curvature. We are trying to relate this. Okay, first in this equation, we will try to relate the few terms like sigma b and r. So we will try to derive the first part of the equation first and then get the second part of the equation. Okay, now for that let us consider a straight beam. Before bending, before applying this bending moment, the beam is straight. So that means I am not applying bending moment, the beam is straight. If I apply the bending moment, then this beam actually becomes a circular arc like this, because you have applied a pure bending. These are the assumptions made in this derivation. So that means initially the beam was straight, there were no stresses in any of the fiber. You understand kinesis? Now this pen I am holding it, there is no stress. If I apply a load like this, there is compressive stress. So that means this beam is there, no stresses, it is straight, and Young's modulus is actually same throughout the beam, and it is isotropic. There are some assumptions like this. Okay, and now you are applying pure bending moment, and when you apply a pure bending moment, it actually turns into a perfect circular arc like this. And an element PQRS considered in this beam also turns into a circular arc, which is actually shown like this. So I can make this look like this. So it is actually shown like this. PQRS turns into a shape like this. And in this shape, you can see that there is what is called as neutral axis. Neutral axis, when you bend, will it expand or compress? Neutral axis, so will it actually expand or compress? Same, it doesn't change because it is exactly at the center. And any fiber above the neutral axis, because of this type of bending, it gets compressed, so that means there is shortening. And any fibers below starts to expand. So whether it expands or compresses, they will have stresses. Okay? So for that, we need to find out the relation between the strain of this member to find out the stress here. So let us, what is the initial length of the fiber EF? Okay, let us consider this fiber EF here also, before bending. Okay, and the initial length of the fiber, please write this. Initial length of the fiber EF. What is the length of the fiber EF? Length of the fiber is equal to the length of the neutral axis in this element. And here you just agreed that the length of the neutral axis here, in this element and in this deformed element is same. Did you just agree with me?
Yes.
Neutral axis length doesn't change. So the element length here and original length before applying the bending moment was same. You know that this distance from this center of curvature to this, let us call it as R. Sorry, not Y, R. Let us call it as the radius of curvature, R. So we know that then this length of this neutral axis here can be given by the formula R into d theta. So you know that length of the fiber EF is same as length of the fiber neutral axis. Length of the fiber of this neutral axis, NA. Length of the fiber as neutral axis So therefore it is actually r into d theta. Is it okay? ಇದು ಅರ್ಥ ಆಗ್ತಿದೆಯಾ? ಸೊ ಯಾವುದೇ ಒಂದು ಲೆಂತ್ ಇವಾಗ ಈ ತರ ಇದ್ರೆ ಇದ್ರ ಲೆಂತ್ ಎಷ್ಟಿದೆ ಅಂತ ಕಂಡುಹಿಡಿಬೇಕು ಅಂತಂದ್ರೆ, if you know this angle in theta or d theta, if you know this radius of curvature r, then you can find this length as r into d theta. Idradu length ಬಂದ್ಬಿಟ್ಟು r d theta ಇದು ಫಾರ್ಮುಲಾ. So here also to find this length of this, so this r is the arc length and this theta is the included angle, and that product will give you the length of this r. So same way I use this r into d theta, so I can use this as capital R or whatever, small r or whatever you want. Here I use capital R, I use this capital R itself. Okay, so I've done this. Now this is the initial length of the fiber EF. This is the initial length of the fiber EF. Can you tell what is the final length of fiber EF? Fiber EF, final length. Initial length is there. The final length alli, now whether the length has increased or decreased? It has increased. So ivaga iದ್ರ ಲೆಂತ್ ಬೇಕು ಅಂದ್ರೆ r into d theta ಮಾಡ್ತೀವಿ. ಸಪೋಸ್ ಇಷ್ಟು ಲೆಂತ್ ಬೇಕು ಅಂದ್ರೆ ಇದ್ರ ಲೆಂತ್ ಬೇಕು ಅಂದ್ರೆ r plus y into d theta. So that gives you the final length of the fiber EF. ಗೆ final length of fiber EF ನ ಏನಂತ ಹೇಳ್ತೀವಿ? E dash f dash ಅಂತ ಹೇಳ್ತೀವಿ. So final length we call it as E dash f dash. So that is actually r plus y into d theta. Okay. Now we know stress, strain, and all this. What is the form? Now what is the formula for strain? What is the formula for strain? What is strain? Change in length to original length. Okay, change in length to original length. So that is our final length. So change in length is final length minus initial length divided by the original length. So original length is this, and a difference of this has to be written above. So that is r plus y d theta is the final length minus the original length. So that gives you the change in length dl divided by the original length, which is actually r d theta. So here you can write this as r d theta plus y d theta minus r d theta divided by r d theta. So here r d theta cancels out. So what you are left with is y d theta divided by r d theta. So here d theta cancels out. What you are left with is y by r. Sorry, y by r. So this is actually strain. And let us not use the word strain here. So let us use the symbol strain. Epsilon. Let us use this term epsilon. So finally we can write that epsilon is nothing but y by r. Epsilon under strain. So call this equation as 1. Okay, is it seen up to this? Illariಗೂ ಕಾಣ್ತಿದೆಯಾ? Okay. Also we know that Young's modulus के formula है ना? Stress by strain. Okay, stress by strain. So here strain is stress by Young's modulus. You call this equation as equation 2. And now you compare this equation 1 and 2. From 1 and 2, How do you get? Sigma by E is equal to y by r. Sigma by E is equal to y by r. And is it actually looking like this equation? Is it looking like this equation? Just we have to swap these terms so that it starts looking like that. Okay? So or we can write this as sigma b. We can actually specifically write this as sigma b. This is actually the bending stress. Sigma b by y is equal to E by r, because the stresses are induced due to bending. So let us call this as bending stresses, and we can write this equation. So in this way, we have actually we have derived the first part of the equation. I mean, one part of the equation. If it is for 10 marks, if you derive up to this point, you get 5 marks. Okay?